So here we have topic 4, graphs and equations of logarithmic functions. So we're nearing the end, guys. This is the second last new topic for the unit, for the course. So we're going to investigate the characteristics of logarithmic functions with base 10 and with base E from graphs and equations. So we're looking at graphs and equations. We're going to do a little exploring. So a logarithmic function is in the function of the form y is equal to a log b of x. B is greater than 0, not equal to 1, a is not equal to 0, and a and b are real numbers. A common logarithm is a logarithm with base 10. And when you have the log button on your calculator, this is what it is calculating. When you write a common logarithm, you don't need to write the base. So when we take things from either side and we say log 7, we don't write the base, we mean 10. Okay? The equation y is equal to log x, therefore is equal to y is equal to log 10, base 10x. A natural logarithm is a logarithm with base e, which we've talked about before, is Euler's number, and it's a constant irrational number that equals 2.718 da 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 da. The equation y is equal to ln x is equal to y is equal to log of ex. Now your calculator also has an ln for natural logs. Okay, so that's what you're looking at. The graphs of logarithmic functions may have many characteristics, right? We've looked at characteristics of graphs before, so we're going to be looking at some characteristics of graphs here. So here are some of the ones that we will be exploring. They probably will sound very familiar because we've looked at these characteristics before, and we're going to just talk about what characteristics are there for logs versus other kinds of functions, logarithmic functions. So we'll look at the value of the x-intercept, the number of y-intercepts, domain, range, and end behavior. End behavior is a function is a description of the graph's behavior at the far left and far right. Okay? And generally we're talking about moving from left to right. Alrighty. Okay. So let's look. Example number 1, exploring characteristics of logarithm functions. Use technology to draw the graph of the logarithmic functions below. Set your windows to the following. So you're going to set your windows like this, and we're going to complete the table. So this is an exploration for you guys to do. So we're doing these two functions, so try them out, and then when you come back, we'll do them together, okay? So let's take a look here. We're going to set our windows. We want 0, 10, 1, and for our y-min, we want -5. Our y-max can be 6, and our y-scale is 1. So that's our window. And we'll go in here. I'm going to clear out these other things from other work. We're going to put in 3 log x. Now remember, I don't need to put anything because the base is going to be 10. And then we're going to graph it. So if we look at this graph, we get a graph that looks something like, oops, I guess I better put it on the right pen. That will help. Woohoo! So it looks like so. Okay, so a little bit different. So let's figure out what we have. Our value of A is 3. Value of B is 10. And we're looking at this as our standard form for a logarithmic function. So it's not an exponential function right now. It's a logarithmic function. So table of values for y. For when x equals 0, y is undefined. You can see that it is approaching. So it's going approaching a vertical line. For 0.1, if I put in, graph, second function, trace, and I put value in. So we're just going to put in these values for x. So 0.1, I get -3. I put in 1, I get 0. I put 2, I get, we can say 0.9. It's 0.903 there. So I can just put 0.9. And lastly, if I put 10, I get y equals 3. Okay, which makes sense to me. Okay, value of my x-intercept. So it crosses, if I put in a 1 here, we can see on our table too, right? Our x-intercept happens when y equals 0. So the value of the x-intercept is equal to 1. The number of y-intercepts, none. Okay, it does not cross the y-axis. The domain, x is greater than 0, but not equal to. And y is in the set of real numbers, because it can go either way, anyway, up or down, right? Okay, so now let's look at the graph of the natural log, and it's negative natural log. So come in here, clear this out, negative ln x. And we're going to graph that. Ooh, so we get a different shape. Okay, probably because we made it negative, just saying. Value of a in this function is -1. Value of b, well, it's natural log, so it's going to be e, Euler's number. Now let's fill in the table of values using trace and value. So when x equals 0, y is undefined, right? Because it's approaching that vertical line. When I put in 0.1 for x, y is 2.3. When I put in 1 for x, y equals 0. When I put in 2 for x, it's negative 0.69, or 0.7 will do as well. And if I put in e for x, and if you look on your calculator, I got to look at mine because I can't see it on the screen to find exactly where it is. Where is my e? Let's just try this. Second function. I'll put e to the 1. Right, yep, that worked. Because e to the 1 will be equal to e, right? And we get a -1. So that's our Euler's number there, the 2.718, blah, 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 blah. Okay, oops. There we go. Now let's look at the rest of this table. Value of the x-intercept. Well, the x-intercept happens when y equals 0. It equals 1. Number of y-intercepts, 0. There are none. Domain, x is greater than 0. And the range, y is in the set of reals. I like doing the double bar. There we go. Okay, so a little bit of an exploration there with those functions, exponent or logarithmic functions. Got to say them right. Okay. Now, what parameter determines whether a logarithmic function is increasing or decreasing? It would be a, the a value. If we look at our two graphs, graph 1 would be increasing from left to right. Graph 2 would be decreasing from left to right. Graph 1 is positive for its a value, and graph 2 is negative for its a value. So let's just make that note. So if a is greater than 0, greater than 0, increasing. If a is less than 0, it's decreasing. Okay. Do you agree with the following statement? Explain. All logarithmic functions of the form f of x is equal to a log bx do not have y-intercepts. Yes. Now we might want to test a few more, but based on what we've seen, we're going to assume that characteristic. Do you agree with the following statements? Explain. All the logarithmic functions of the form f of x is equal to a log bx have a restricted domain. This is true. X has to be greater than 0. Okay, we don't have anything where x is less than 0. So let's use an equation to determine the characteristics of a graph. Determine the characteristics of a given logarithmic function. Verify using technology. So here, our value for a is 12. Here, it's -3. Our value for b, this is a natural log, so it will be e. Here, we've got log, so it's going to be 10. There's no base written in. X-intercept, well, based on what we saw before, is 1. 1. Number of y-intercepts, none. Now, we're going to test this with our technology in a second. None. End behavior goes from 4, to 1. Yep, 4 to 1. And here it goes from 1 to 4 because it's negative. Okay, this is we're guessing based on what we've seen before. Increasing or decreasing, we've got a positive value for a, so we're going to say increasing. Here we have a negative value for a, so we're going to say decreasing. Domain, x greater than 0, x is greater than 0, and the range y is in the set of reals. So let's test those and let's see if that is in fact the case. So we're going to clear, oops, oh, my y equals, we're going to clear this. For the first one, we have 12 ln x, and let's graph it. So value of a was 12, value of b is e, x-intercept is at 1, so let's test that. So second function trace value, if we put in a 1 for x, yes we do, we get y equals 0. No y-intercepts, right? Does not cross the y-intercept, the y-axis, sorry. It goes from 4 to 1. It's increasing. X has to be greater than 0, and y is in the set of real numbers. Okay, now let's test the other one. Just to make sure, doesn't hurt, -3 log x. And we're going to graph that. So let's check. Our a value is -3. Our b value is 10, because that's log base 10. There's one x-intercept, right? Number of y-intercepts, there are none. Y approaches 0, but does not actually touch it. Or sorry, it approaches, y does hit 0, but x approaches 0 and doesn't touch it, so there's no y-intercept. End behavior, it goes from 1 to 4, decreasing. Domain, x is greater than 0, and range y is in the reals. Now we want to check our x-intercept, second function trace value. Let's put in 1, see if that is indeed our x-intercept. Yes, it is, because y equals 0. So we're finding a few characteristics that are consistent. So, reasoning about the characteristics of the graphs of logarithmic functions. For each set of characteristics below, write an equation of a possible logarithmic function. Natural, decreasing, logarithmic function. So, if we want it to decrease and we want it natural, we could have y is equal to -7 ln x. It could just be y is equal to -ln x, and it would still be decreasing. It could be y is equal to -572 ln x. So as long as that a value is negative, right? So a is less than 0. Okay? End behavior extends from quadrant 4 to quadrant 1. So if it's going from quadrant 4 to 1, it's increasing. Right? So And it doesn't say whether it's a natural log or another kind. So y is equal to log x. That will work. Y is equal to natural log x. Y is equal to 7 log x. Log x. As long as it's a is greater than 0. Okay? Passes through the point 10, comma, negative 3. So that means this would be our x value and this would be our y value. So how do we know where it's going to go? So basically we want it when x equals 10, y equals negative 3. So if we go y is equal to negative 3 log of 10, log 10 of 10 equals 1. Right? So I can write in my little base there. Because basically it has to be a log that is going to be equal to 1. We times it by negative 3. That will give us 1. So this, if we put negative 3 log of x, then that means when I put in a 10 for x, I will get a negative 3 for my y. Okay, a little bit more thinking there. Okay. Match each graph with the correct function. Justify your reasoning. Okay, so let's take a look at these. These would be good ones for you to figure out. Pause video and then come back and see if you're right. Okay, so first one. We know that we are decreasing. Oh, these are exponential functions, aren't they? That's okay. Some of them are. So if they're exponential functions, let's see, 3 is an exponential function, right? And so what is an exponential function that we have that would fit, right? So is this. These two are exponential functions, right? Because they fit that pattern. So we need to look at our y-intercept. So here it looks like our y-intercept is around there, which would probably be, it looks like a 5, right? So I'm going out of order. So this would be y is equal to 5 to x. It's also increasing, right? So y-intercept equals 5, and it's increasing, okay? And it's an exponential function as opposed to a logarithmic function. Here, my y-intercept looks like it's at 2. So I've used this one. This is the other exponential function, and it's decreasing, so that fits. So it would be sorry guys, y equals 2 times 0.1 x. So justification, the y-intercept equals 2. It's decreasing. So b was greater than 0 but less than 1.1, right? And it's an exponential function. Now, how do we figure out the other two? So that one's done. Well, I think we just need to look at whether they're increasing and decreasing, right? This one here is decreasing. So it's going to be y is equal to negative 2 ln x, right? It's decreasing. And it's a log, right, based on that shape. This one, so that takes out this one, would be y is equal to 6 log x. It's increasing, and it's a log function. Okay. Neither of them have y-intercepts, So they can't be those. So a little bit of an examination of graphing of logarithmic functions. Logarithmic functions have the form y is equal to a log bx, where b is greater than 0. It's not equal to 1, because that would just be a constant. And a is not equal to 0. A and b are real numbers. The parameter a determines our end behavior. If it's greater than 0, it's increasing. If it's less than 0, it's decreasing. Parameter b is the base, where b is greater than 0, b is not equal to 1. Now, we mostly just looked at the 10 base, but same basic shapes. There's two different shapes. One is increasing, and one is decreasing. And again, we talked about the fact that they're dependent on a. All logarithmic functions of the form y equals a log bx, where b is greater than 0 and not equal to 1, and a doesn't equal 0, have the following characteristics. The x-intercept equals 1. There are no y-intercepts. End behavior goes from 4 to 1, or 1 to 4, depending on whether it's increasing or decreasing. The domain, x is greater than 0, it's restricted, and y is in the real numbers. So this has restrictions, right? That's what that means. Okay. Common logarithm with base is a logarithm with base 10, and a natural logarithm is a logarithm with base e. Okay, and it's written as ln x. Okay, and that uses Euler's number. Okay. The graph of log 10x is a reflection of the graph of y equals x to the 10. So let's see what that looks like. That's kind of an interesting thing we didn't really explore, but it's kind of neat to look at. So I can turn this on. I'm going to clear this. Clear. I'm going to change my window, and I'm going to give myself a negative 10 here, and I'm going to do the same thing here, where I'm going to go negative 10, 10, because I'm going to graph log of x in this for y1, and for y2, I'm going to graph 10 to the x, so we can see what they look like. So we graph those. This is the first one is our log, and our second one is our exponential function. So that's kind of an interesting thing to look at in terms of that they're a reflection of each other. So if you folded it, you would get the same thing. Okay. Alrighty. So second last new topic. Enjoy. You're going to do some practice with that tonight, and might start a little review with you.